Okay, so as I told you, first we'll be discussing optimization methods in this course. So let us see the points one by one. Uh, of course, I don't suggest that you do slides in this way. It is just that I wanted to cover some materials in fewer slides. So you can see that the optimization methods we will be learning in this module of the course. We'll be discussing about the relationship between optimization and deep learning, as well as the challenges we are facing when using optimization and deep learning. So for a deep learning problem, we usually define something known as a loss function. So yeah, how many of you know about this loss function? Anyway, so once we have that loss function, we minimize this loss. To minimize this loss. So in optimization, you can see that a loss function is often referred to as an objective function in the optimization case. So the loss function you are referring in deep learning is is a synonym in case of an optimization problem where instead of a loss function, you are saying it to be an objective function. So in optimization problems, you will never say or maximize the loss function. We will say minimize the objective function, maximize the objective function. Objective function is our keyword in optimization. So by convention, mostly by convention in the books everywhere here, we always say that minimize an objective function. Minimize. Okay, minimize the objective function. If you want to maximize, what you will do? Just flip the signs. Flip the signs. Minimum of fx, minimum of some f, minimum of some f is negative of is equal to negative of maximum of f, isn't it? I will tell you why that is the case. Morning, yeah, I will tell you what is the case. Yeah. So yeah. Just 1 minute. Let us. Okay. So yeah. So yes, you can see that although optimization is the loss function for deep learning, the goals of optimization and deep. So you can see the goal of optimization is primarily concerned with minimizing an objective function, whereas the goal of the deep learning problem is finding a suitable model with a given amount of finite. Which model can maybe fit or works with your finite amount or can do certain predictions. Okay, but the primary objective of optimization is to minimize or maximize the objective function. It has nothing to do with the model as such. But deep learning is usually about the model. Which model efficiently can classify, which model can efficiently predict certain things. So there are two terms which I will show using Python now. Is about training error and generalization error. Okay, there are two terms: training error and generalization error. What are these? So usually, training error is different from the generalization error. Usually, it is confused to be the same. So you know that in deep learning, you are doing the training process. Number of epochs, number of forward propagation, back propagation, and all these things. It is training on your data. It is training on your data. The amount of finite input data you give, it is training on that input data. Okay, and it won't be generating some kind of training error. There will be some kind of training error. Then there is some other term which is known as a generalization. What are these two? So yeah. So you can see that the objective function of the optimization algorithm is usually a loss function based on the training data set. And our goal of optimization is usually to reduce this training error, to minimize this training error. So you can see our objective function is now the training error. Okay, because you have to minimize it, minimize the error. Okay. See the last line here. However, the goal of deep learning, or more broadly statistical inference as such, is to reduce the generalization. Okay. So deep learning aims to reduce the generalization error, whereas optimization problem aims to minimize the training error. I suggest when you go back home, try to know about the difference between the training error and the generalization error. Okay. So what is the difference between the training error and the generalization error? Okay. So yeah, to accomplish the latter one, that means the deep learning one, we need to pay attention to overfitting in addition to using the optimization algorithm, okay, to reduce the training error. So you, in solving the deep learning issue, you don't have to only rely on optimization algorithms. You have to rely on optimization algorithms in addition to plus the overfitting issue. There are two issues you have to take care of. Okay. So therefore, where overfitting comes, you can see that regression will come. Anyway, so I will show you two examples here in Python. Yes. So you will be considering about something known as empirical risk and the risk. So there are some terms I would like you to learn and come to the next class. That is, one is training error. What is training error? What is a training error? What is a generalization error? What is a generalization error? What is a risk? What are empirical risks? I want you to learn each of these terms so that these terms don't appear to be blank to you whenever you hear about it. Okay. So yeah, one such is empirical risk and the risk factor. So empirical risk is nothing but the average loss on the training data set. Average loss on the training data set. Just see that empirical risk is local phenomena, that is, it bothers only about the training data set, whereas the risk is the expected loss on the entire population of data. Okay? On the entire population of data, you can see that the risk factor is behaving globally, like it is depending on the all population of the data set, whereas your empirical risk is only depending on the training data set. Okay, fine. So due to this motivated, we define two functions. One is known as a risk function f, and another one is the empirical function g. Okay. So in the Python, I will show you that I have explicitly considered to using those two functions. I can show you that what are these f and g. So our focus in this course will be mainly our focus on this course will be mainly on the performance of these optimization algorithms in minimizing the objective function rather than a model's generalization error. So we are not much concerned about the generalization error. That is much more will be taken care of in your future deep learning course. Okay, we are much more interested in minimizing the objective function and the performance of optimization algorithms in reducing the training error. In reducing the training error. Okay. So in deep learning, most of the objective functions are complicated and don't have analytical solution. One of the reasons why one of the reasons why we are learning numerical methods for them. Therefore, the course name is numerical methods and not analytical methods. Analytical methods mean you can find a formula for the minimization. You can say that if we fix z equals to 2, x equals to 3, and y equals to 5, then the training error is minimized. Like, sorry, z equals to some value like z plus or xy, something, analytical solution. But what you are actually seeing is actually a numerical method to solve those things, because these are not analytically solvable. Why it is analytically not solvable? Because that's the kind of problem you are facing in deep learning. The kind of problem you are facing in deep learning, most of them are not tractable analytically. Okay. Why are we doing looping process in forward propagation? We could have just written one function like which can do a loop analytically, some formula, and apply to it. Why we need to do a for loop? We are doing everything numerically in deep. Okay. So this is where we come across something known as numerical optimization algorithms. So you know how these are very different from the optimization stuff you have learned in your high school or anywhere else, where you just have the equations and you try to solve. But however, in this course, we will take equations to understand. We will take equations to understand that concept. But of course, you can apply it on a data. Of course, you can apply it on a data. But to understand for the first time, we will take some equation examples, like minimize this function or something. And to know the method, you have to digest that. So the optimization algorithm in this course fall into this category. Okay. So yeah, before that, I would like to pause. Okay, so here you can see that just before the lecture, just before this break, I told you about training error and generalization error. Okay, training error and generalization error. So here just an example. Here just an example. Here just an example. Like what is f? What is g? So you can definition f of x, it will return for any x, it will return x cos pi x. Okay, and the function g will return the function f plus some noise, plus some noise. That noise is something I have taken is 0.2 cos 5 pi x. Okay, I want to plot these two. I want to plot these two functions f and g. I want to plot the functions f and g. And what do you think? Those two are the same functions, right? Those two, function f is like x cos pi x, whereas function g is the same, like x cos pi x plus another cosine term. So nothing much should change, right? Nothing much should change. Addition of these cos terms or sine terms you would have faced in your semester while dealing with DFT. Okay, there's a summation of sine and summation of cosine terms. So what do you think how this function looks like? Maybe I'll ask the question, will the function, if the function is there will be maximum minimum. For this function at least, cos, you know, cos function is an oscillatory function. It has a maximum of 1, it has a minimum of -1. Yes, now my question is, the function f and g, do you think they have the same minimum? Can they have the same minimum? What is? How many of you think the minimum is different? Not the trivial. Not the trivial. Okay. Okay. So in the next part of the code, I am just plotting. I am doing the beautification of my plot. Nothing more. I am just doing the beautification of my plot. How the plot will look more attractive to me. Okay. So that's part of um, data visualization in the sense. There's a part of showing your data much more in an appealing way. Okay. Why we are saying that when you do, suppose I have a library and I purchase books from different vendors. So I'm keeping all the list in my Excel file, and I want to know which company sells to me the book in a cheapest price, that is more discount, and the delivery time is also less. Then I will prefer that vendor. Okay. How I will know that? I have to learn from the data I have. From that data in Excel file, I will transform it into pie chart or a bar chart in terms of time, in terms of discount. Then the bar chart, with seeing the bar chart, I can know which company sells me at a more discount and faster way. Okay. So like that, I want to beautify. That is known as a that is known as a dashboard. That is known as a dashboard where you keep all the plots together. You can do it by what do you call? Or you can do it by which kind of softwares? Power BI, Tableau. Another one. Studio. Yes, you can do it by Looker also. Looker. So Looker is a new platform, not a new platform, old one, but I suggest try to look up on that also, like Looker Studio. So Looker Studio is more intuitive a bit. Okay, so try to do that. So here also I am just so that it is appealing to you and attractive to you. You can see this is the plot with boundary sizes. I have given that usually the plot is open boundary, but I have drawn a box around it to make it look more attractive. And the X labels, X fonts are also a bit bigger. And most importantly, I have drawn these labels. Okay. So this is not the correct label actually. This is the point I wanted to attack, but it showed this one. Try to see this point. So you can see this is the f of x in blue and this is the g of x. You can see that the minimum of f of x, which is the risk we are saying, minimum of the risk factor. So f is a risk. F you can say is a training error function. Okay. G is also the generalization error function. So you can see the minimum of two of the errors are different. The minimum of the two of the errors are different. They are not the same. So therefore, if you want to learn optimization, the error occurring in deep learning, you want to go for training error, okay, and you can use the optimization methods. If you want to know more about generalization error, then yes, the optimization method might not be useful that much. Okay, you have to, yeah, you will learn more methods in that course. Okay. So you can see this is known as the empirical risk when you are considering the function g around one. This is known as the minimum of empirical risk. Whereas in blue, you can see this is the minimum of the risk. Empirical risk and risk are different. As I told you to know about these terms. Okay. Fine. So you can see it should be above actually. The graph, read as graph above. The graph above illustrates that the minimum of the empirical risk on a training data set may be at a different location from the minimum of the risk that is in the generalization. Okay. So try to make yourself convinced. You might be confused a bit about training error and generalization error. It's normal. I suggest go back, try to know what is generalization error, what is training error, where they are different, why they are different at a deeper level. Now is a good time to know about it. Okay. So yeah. So what is a local minimum? So given a function, I think this function is x cos pi x. Yes, you can see this is the function x cos pi x. I am plotting it. So not much of these codes are needed. These are all to beautify your plot. Okay. Annotate you can use to put a line, to put an arrow of which color, at what point, the coordinates you can give. So I'm giving the coordinates here. You can see minus 0.77, minus 0.5. Okay. So at this value, I want you to put an arrow, and I'm telling Python to write something near that arrow. What I'm trying to write, local minimum, global minimum. So you can see it's doing the same thing. Near that arrow, it is plotting all these things. So like this, you can beautify a plot. So why I'm showing you all this is I expect that from you also. Okay. So how I expect that from you? So there will be capstone project in the class. I will show the topics today. So whenever you will do any Python related things, whenever you get a plot, you have to do the beautification of the plot in this way. Okay. But here I don't want the green line to be just a plain sketch would do. Just a sketch like this. Yeah, just a tiny one. Not thick lines. Here in the class I have done. Okay. Anyway, so you can see this is the function f of x, x cos pi x, and this is the function in blue. It is oscillating. You can see this is a minimum. This is a minimum, definitely, but this is a local minimum. It is a minimum from this point to this point. But if you consider the x value from here, follow the cursor from here to say here, then there is a minimum which is less even this one. Which one is this? That is this one. This one is known as the global minimum. Find an x where fx is the least of all considered in the whole domain of your definition. That is a global minimum. Okay. So through this you can know what is a local minimum and global minimum. Okay. These local minimums are usually troublemakers. Okay. The global minimums are usually the troublemaker because what you seek in an optimization algorithm to reduce the training data set is the global minimum. You don't need the local minimum. You need what is the minimum, least possible risk you can take or least possible error. So therefore, you actually want this guy, the global minimum, but actually when you are training your data set, it is very likely that you will stuck here. And when you will be stuck here, you are stuck there. Okay, so that's what I told. In order to reveal this person from the stuckness, you have to push an error. You have to push a noise. Once you put a noise or a penalty function, this point moves away, and once it moves away, then it gets attracted to this global minimum, and you reach your desired solution. That is your least amount of error. Okay, so then you know what number of training layers, what number of hidden layers, and all these parameters, hyperparameters I can set so that my training error is reduced to a global minimum. Okay. So hope you understand it. Understood, right? No? How many of you didn't know it? Is it okay? This is the very easy start. Okay. We'll see. Okay, this one will come later. Let us see something more. Okay. This is what I meant here. This is what I meant here. This is what I meant here, saying like the risk function and the empirical function G. These are the two I wanted you to tell about. Okay. Now let us go. What are the, now we are looking at the challenges in optimization theory for deep learning. While using the optimization methods for deep learning, what are the challenges you will be facing? One is about the training error and the generalization error. Okay, that you will face. Another is two more things. One is a saddle point. One is a saddle point. Can anyone tell what is a saddle point? Saddle point is like a chameleon. How many of you know chameleon? What is a chameleon? Tell. Uh, yes. So insect which changes color. So it's like a lizard, right? Long tail. So why it changes color? It is known as a camouflage. Why are you laughing there? What happened? What you tell in Malayalam? Huh? On the. So they change color. That means you say like a person is a chameleon means like the person is not believable because he changes color. He or she. Not never always not he or she. It can be she also. So they change color. They change color means they change their behavior. Not only with human beings, mathematical functions are also like that. Okay. So mathematical functions also change their behavior. Oh, saddle. Has anyone seen a saddle? Where? Have you seen horse? How many of you rode on a horse? Mr. Sandeep, yes. Mr. Adil also. So how you rode on a horse? You sat on a horse, right? Huh? You sat on a horse. When you sat on a horse, you did not sit on the skin, right? It was a you call leather sheet, right? What is that leather sheet called? Yes, it is called a saddle. Why it is called a saddle? Anyone? So the leather sheet is called a saddle because yeah, so you can explain like yeah, maybe we'll see the Python code and I'll ask you. Okay. But this is the saddle point is once a challenge. Global minimum is not the only troublemaker. Saddle point is also a troublemaker in optimization algorithm. Okay. So there are many challenges in deep learning optimization. Some of the most vexing ones or the most challenging ones are local minima, which you learned about now. That what is the issue? Another is saddle point, and another is vanishing gradients. Vanishing gradients. So there are two more things we will learn about: saddle points and vanishing gradients. The objective function of deep learning model usually has many local optima, which you can agree that maybe the function looks like this. Maybe the function looks like this. Isn't it? If the function looks like this, can you tell me what are the global minimums? Sorry, the local minimums. This is a local minima. This is a local minima. This even is a local minima, right? But there is one single unique global maximum that is, sorry, global minimum, which is this. Okay, you got that, right? So therefore, there can be many optimum. Local optimum means it can be a minimum or can be a maximum. Local minimum or can be a local maximum. Similarly, this can be a local maximum. This can be a local maximum. Or maybe here I can go this side. So this can be the global maximum, but these two are the local maximum. Okay, fine. So when the numerical solution of an optimization problem is near final iteration, may only minimize the objective function locally. That is the main trouble here. You want globally to be minimized. Once you get stuck in local minima, you are stuck. You need other methods to strike it away from the local minima. So rather than globally, which you want, as the gradient of the objective function approaches or becomes zero. Okay. Right. So only some degree of noise, which I already told, might knock the parameter. This is what I told you before, right? In fact, this is one of the most beneficial properties of the mini batch stochastic gradient descent. This is one of the most important properties we will be using in the mini batch stochastic gradient descent. There we will see that how, if you are getting stuck at a local minimum, which you will get stuck, how you can use, how you can knock out the parameter, how can you use a parameter so that it can knock out from that local minimum to pass it into the global minimum. Okay, this we will learn mini batch stochastic gradient descent. Okay, where the natural variation of gradient over mini batches is able to dislodge the parameters from the local minima. I think it's a very interesting topic. Okay, very interesting topic and very much important also. For example, for a saddle point, let us see about a saddle point. Can you tell me an example of a saddle point? A very easier one. Like I don't want a very complicated one. Very easier one. Easier one. Any ideas? Any? You know about a saddle now, right? I will tell you. I'll tell you one example. Consider this. That is x. This is y. And suppose you have a function. How y x cube looks like? How y equals to x cube looks like? For positive x, y will be positive, right? If you put on positive value here, it will give you positive y. If you put negative x, it will give you negative y. So therefore you can say that the function values will be in these two quadrants only. This will be empty. These two quadrants will be empty. I'm training you how to plot this. Okay. So you can see that, yeah, you can try to understand how the plot is, but the plot will be something like this. I did not do it very nice. Yeah, still not nice. Still not nice mathematically. Okay. So this is the y equal to x cube plot. Okay. Now I suggest, what is the minimum here? Can you tell me? What's the minimum? When you run your functions, optimization functions on this, optimization method on this function, y equal to x cube, the optimization method will get stuck at a point. It will get stuck at, it will get stuck here. It will get stuck at x equal to 0. Why? Why it will get stuck at x equal to 0? It will get stuck at x equal to 0 because x equal to 0 is a saddle point. It is neither a minimum, because a minimum you can have as much as x grows. Okay, as many as x grows on the negative side, you can always have the minimum there, right? So therefore, no minimum is there, but still. So if you think that local minimum is the only thing bothering optimization, you're wrong. There is something more, that is saddle point. Even though there is no local minimum here, anything like that, still it is failing. Your method, optimization method, is failing because of this saddle point, y equal to x cube. This is a simple 1D example. Then we will see in Python a 2D example. That is a mathematical function that is on a surface, maybe x square minus y square. How this looks like? How this function will looks like? We'll see in Python now. And why it is a saddle point, we'll see. Okay. So I want to convince you that saddle point is a troublemaker in optimization methods. Okay. One more is there, but we'll see that. Let us go back to Python. Yes. So here you can see. Here you can see. I'm just taking y equal to x cube here. The function in the range of -2 to 2 in the grid size of step size of 0.01. Okay. Okay. So I'm plotting it. All our beautification rest. So you can see, yeah, I prefer this actually. I prefer this one. The arrow size, I prefer this one. This is very nice and soft looking thing. Easily convincing. Other are very intimidating, like easily caught to eye. So you can see that this is a saddle point. Why this is a saddle point might be confusing, but when you look into the two-dimensional thing, it will be much more convincing. Now I told you, let us look into x square minus y square example. So now it will be a three-dimensional plot. It will be a three-dimensional plot, that is z equals to x square minus y square. You have to plot x, y, z. You have to plot this x, y, z. Sorry, z. This is x and y. Okay. It will look like a surface. How it will look like? Any ideas? So we are creating a 3D plot. For that, you have to define mesh grid. See, you have to define a mesh grid. I think you already know about how to plot this, right? How you do? You first create the input values. What are the input values? X and Y. This is a mesh. This is a mesh, right? Now in this mesh, each of these points, you are trying to evaluate what is Z. Yes. So this I am doing it here. And where is my, where it went? Again got stuck. Finding that bar, slide bar. Where is that slide bar? Huh. Okay. Okay. So yeah, all our beautification else. Yeah. This is the function. This is the function, how it looks. You can or saddle. Now Mr. Adil and Mr. Sandeep can say, did you sit on this? Yeah, they sat on this. So you can see, and even I think the potted. So no, this is no, not a thing to be laughed. This is the business strategy. This is the business strategy. This is why you like the chips. This is why you like the chips. Why why some chips company, like, yeah, don't name it, but still they have it like this, right? Why potato slice is flat, right? Just put in oil, flat, you will get it. Why so much complexity, like so much, such heavy companies? Why? The idea is so when you make the chips and put the seasoning and all, the better chances are absorption of here. Like if you have a saddle structure like this, first of all it will taste good. Definitely. Second is the absorption of different spices is maximum at this rate. Okay, none of the sides will be missed. If it is flat, when it is going through the belt, it will always be on that side. You have to put lot of pressure on that to flip it on the other side. Okay, but if you have this kind of structure, just a small push can invert it also. So try to see, there is actually a theory behind this, why they are made in this shape. Okay, I want you to learn about that. So anyway, this is a horse saddle. You can fall on this side, you can fall on that side also. Okay, so if you pass on a ball from this side, it can go this side. If you put a ball on this side, it can go on that side. So there are two directions. Therefore, it is a saddle. In one direction, it is like increasing on one direction. On the other direction, it is decreasing. Sorry, it is decreasing. So therefore, the middle point of intersection of all those directions is the saddle point. So you can see this saddle point is 0, 0. Okay. So yeah. So this is what is a saddle point. If your optimization function, this is a mathematical example. I am not saying your optimization method will fall into this function. No. One such function which looks like this. There can be data where your data, when you plot, it will look like this. Okay. Data will never flat, right? Your data won't be never flat. It will be ups and downs, valleys. So it might be that you encounter a saddle. Definitely you will encounter a saddle, a valley. So therefore, in those cases, optimization method will fail. Saddle point. I told you, it is not a local minimum also, but still it fails because it is a saddle. Because it's a saddle. Anyway, let us look into another function, tanh. This you can relate, I think. I hope many of you already know now that in training neural networks, you use activation functions. And in activation functions, you use lot of, there exist 1000 or 10,000 of, maybe 1000 of activation functions. So one of them is the tanh function. Old one, previously used function, activation function is a tanh function. Now people are using ReLU. Functions. Okay, ReLU is more efficient than the tanh. Okay, why? Why ReLU is more often used than tanh? This in next course of deep learning, you will just use ReLU. You will use tanh, and you will suddenly see that ReLU is more efficient than tanh. But why? That will be a question that we will answer here. Okay. So let us come to the next one, that is vanishing gradients. Let us come to the next one. Like besides the local minima, now you know that there are two troublemakers till now. Local minima is one, the saddle point is one such troublemaker. Another troublemaker is vanishing gradients. Is the third troublemaker, that is for optimization problems, vanishing gradients. So yeah, what is a saddle point? Here is a definition just for everyone to look at. It's any location, saddle point is any location where all the gradients of the function vanish, but that point is neither a global or local minimum. Okay, can you see that in x square minus y square? Let us look into z equal to f of x comma y, that is x square minus y square. Can we, so this is a function of more than one variable. You have to use partial derivatives. For the x case, you can set dou by dou x of that f of x comma y to be 0. What you get from that? dou by dou x of x square minus y square is, what you do? This will be 2x, y square will be constant. If you are differentiating with respect to x, y will be constant. So it will be 0. So it is 2x. And that you set to 0, right? If you set 2x to 0, what you get? X star equal to 0. So this is a local minimum in your case. Now if you do the y case, what you will get? Dou by dou y of f of xy equal to 0. What does that give? Dou by dou y of minus 2y, because you are treating x to be constant, equal to 0. So that gives y star equal to 0. So you can convince yourself that this is this a local minimum? Tell me, is this a local minimum? How will you know? This is one of the assignment that you try to go in deep about this function. I have touched some of the most important parts, but some of the remaining parts are still not known to you. I suggest you do this kind of calculation and try to understand the full literature on experiments. Okay, and try to see why the gradient vanished at 0, 0. Why the gradients vanished at 0, 0. Okay. Anyway, so that's the saddle point. Let us come to vanishing gradients. So this is the most insidious problem actually. So to encounter is the vanishing gradients. So recall our commonly used activation functions and their derivatives. So you can say that our most commonly used activation function, one of them is tan h. Okay, so we want to see what is the problem with tan h. So for instance, you can assume that we want to minimize the function tan hx. Ignore this is the latex command I wanted to type. So f of x equals to tan h of x. And suppose we started from x equal to 4. Our starting point is x equal to 4 in the tan h function. Now we will see using Python that the gradient of f is close to 0 in that case. Okay. More specifically, if you compute the derivative of that function f of x, you will get 1 minus tan h square x. Okay. That is like sec h square, right? This you should know. This you should know. Okay. Try to see. So therefore, if you compute f prime at 4, it is coming to be 0.0013. It's close to 0. Okay. So consequently, therefore, since your gradient is vanishing, I will show you using the plot. Just know that when you use tan h function as an activation function in your neural network, and suppose by mistake you started at 4. If you started at somewhere else, you are lucky. But somewhere if you started at 4, then you are approaching to the vanishing gradient region. Okay, we'll see why that is the case. Then if you are approaching that region, then your optimization methods will get stuck for a long time before we make, okay, before you make progress. This turns out to be one of the reason why while using training the deep learning models, it was quite tricky prior to the introduction of the ReLU activation function. Okay, before using the ReLU activation function, people would have get stuck. People would have get stuck more often while using the tan h function. This is one of the reasons why after ReLU was invented, ReLU became the most prominent one than the tan h. Now everyone is using ReLU wherever. Even my students, so some project when they are doing the project on image encryption, for the cyber security, like you have to encrypt the sensitive images, you have to encrypt some biomedical images, that the iris and the fingerprint images of yours are very sensitive, because nowadays as the modern era progresses, you use your iris. Maybe I see in many of the movies and in many of the series and many outside India, they have used iris lock. Even your phone, right, you use fingerprint lock. So once your fingerprint image is being taken off, then gone. You can always print that image on a sellotape, and you can use that sellotape on the phone or the laptop, and you can unlock the system and get hold of sensitive information like bank account details, everything else. So therefore, such kind of encryption is usually essential. And in those encryption, nowadays, some of the students they did as a project, they used CNN, they used convolutional encrypt and decrypt the images. Okay. And during those choices in that CNN, they have used ReLU as an activation function. So you can see that yes, ReLU has been quite famous in this case. But anyway, let's Python one. Yes. So you can see this is the function of tan hx. You can use this one, or you can use even the Desmos to convince yourself that this is the function plot. You can see that where it is. Yes. The moment you are here, you are follow the cursor that neither way it is 0 and your training is happening very smoothly. But somehow when your parameter is chosen such a way that you lie here, maybe in this region 3 4 or 2 3 4 region, you can see that it is approaching a vanishing gradient. The slope is getting 0 slowly. Okay, so you can see this is the place where your optimization algorithm will get stuck. Convince yourself by drawing the ReLU activation. Now I've drawn the tan h function. I have not drawn the ReLU. Draw the ReLU function. Draw the ReLU function and compare that why ReLU is more better than the tan h in activation function. This is a viewpoint from the optimization piece. From an optimization point of view, you can tell why ReLU should be used and not tan h. Okay, so these kind of things you can expect in the exam. Okay, so yeah, this is one such case, and yeah, this is the vanishing gradient. Okay, so this till now is just the introduction part of optimization. I am still motivating you that what is optimization, why optimization has some connection with deep learning, and why are we learning about optimization. We are using optimization from a viewpoint of deep learning, like some questions which you will never get an answer in any other course. Okay, in a deep learning course, they might not say to you that yes, we are facing local optimization, local minimum. Those words won't be used. The words will be used is number of training layers, number of input layers, hidden layers. See, this is the epoch, this is this, you're getting this. Okay, so now you're seeing an optimization perspective on that. Okay, so this is what makes this course a bit more different from any other 5 year back numerical method courses or 7 years back numerical method courses. So to me especially numerical method course was not taught like this. Numerical method course were mostly mathematical in the sense that this is the method, you just solve it and do. But the motivations like this and connections to deep learning were absent. Okay, this is where, keeping in mind the today's generation, I want to develop this. So this is one such thing. Now we'll move to something more important, that is something more interesting now. Before that, just a bit of a subject break, and we'll come to the capstone projects. So